Hi everyone, my name is Emile Kraus. I'm in the Department of Physics and Astronomy, and my talk today is titled Physics of SpongeBob. So, what is the cartoon character based on? What is a sea sponge? They are animals. They're very ancient animals. They're not plants. They come in a wide variety of shapes, sizes, textures, colors. They are basically a moment of active metabolism between the unused half of the universe and the used up half. Because these vast arrays of shapes that they do take on seem to be maximized and tuned to filter as many small food particles out of the water as they can. And so, at the bottom of the ocean, they experience forces due to moving water velocity. And so, at small velocities of about 1 meter per second, they experience a shear stress of about 1,000 Pascal, which is just a force per unit area. It's a convenient unit we like to use. And again, at this maximum velocity, it taps out at about 10,000 Pascal, 10 kilopascal. Hopefully you still remember that number, because again, it is very important. Because when you go to the doctor and they take your blood pressure, hopefully they tell you, if you're healthy, that it's perfect, 120/80. Again, this is in millimeters of mercury. If we convert it to the units we like, 10 kilopascal. Maybe no surprise, if we look at how these things are made and what they look like inside, here's the circulatory systems of more familiar animals. A fish, an amphibian, a mammal, and we see a transport system that is used to get our oxygen and nutrients into our blood and into our organs that we need to live and grow. And here it is for the sponge. So we see the same type of thing, water flowing through their canals, they filter out the food particles here, and out goes the water again. And so what I want you to notice here is this beautiful thing that the sponge, in some sense, seems to be the negative space of our mammalian bodies. And so just as the ocean around the sponges flows around them and within them, we almost quite literally have an ocean inside of us. And while sponges use that large energy that the ocean can provide outside of them, we provide it within us with our heart. It's no accident that our hearts beat and pump just as tidal flows ebb and flow due to the moon. And so, as I said, sponges come in this wide variety of shapes. When that energy source is outside the animal's body, you get more variations on this theme, right? We all look the same. We can't have all these crazy forms, from perfectly spherical ones to giant barrel-shaped ones that a diver can fit their whole torso in, to blobby ones, to conical ones. And so basically what we're trying to get at is, now I've hopefully motivated, what are these rules? What are these rules that inform the growth of these animals? And so to start to get at this question, what do I actually do day to day with the sponges? Well, first and foremost, I actually consider myself a rheologist. So what is rheology? It's literally just you pull something, you push it, you pull it. What does the material do back? And what does that tell you about what this thing is made of and how it lives? And so how you do this, the machine you use is called a rheometer. It actually just looks like a fancy curing machine, doesn't it? It has a top plate and a bottom plate between which a sample is placed. And in the literature, I've seen some crazy things being put in rheometers. Fluids, foams, toothpastes, food, even human feces. So a sample is put between here, and the plate pulls on the sample more and more. The sample pulls back more and more. And there's a time delay between that. And actually, surprisingly, that time delay can tell us a lot about, again, the material and what it's made of. And so what we call these material properties are G prime and G double prime, which is just how springy the material is and how flowy the material is. And in general, those things can depend on the frequency that we're shearing it at and how hard we're shearing it at. And so when I do this with sponges delivered from Florida, I stick them in the rheometer and I see what it does back. And so if we plot those G prime and G double prime as a function first of, let's see what it looks like as a function of how hard I turn that top plate, this sigma naught here. So this is just how hard I'm turning it. You can see there's a region where the material properties, G prime, double prime, aren't changing, but there is some critical shear stress at which these properties vastly increase. And so, okay, a more familiar, this is called shear stress stiffening, by the way. A more familiar example of this is if I pull on my ear, which is made mostly of collagen, as are sponges, my ear doesn't fall down to my shoulder, okay, thank goodness. The material properties change the more I pull on it. They aren't flat. And so I'd like to argue that this is actually a property in general of soft living tissues, because we actually see it pop up all over at all sorts of different scales of life, from tissues of the sponge inside of us, but also inside cells, so at even a much smaller scale. This is data for inside a cell. Again, we see the same sort of thing. For some different level of shear stresses now, they're overall smaller, we see they're not changing, and some critical shear stress, they want to stiffen. And ultimately, this is a mechanical design in order to keep your body together. And so, what I want you to kind of take away from this is that in general, we can come up with these rules, these mechanical rules that are variations of a similar theme here. And so over here, we are mammals. I talked about the sponges, they're here. But in general, I would like to show in my career that there is some sort of unifying theme here for soft matter tissues and growth. And so what I would like to never forget, though, is that where we all came from, and that's SpongeBob's home in Bikini Bottom.